All right, so welcome to the last little bit of your lecture 14, which was for Thursday, March 1st. So where we left off, we just went over in general how transformation works, or how we might take a donor cell, break it down, and transfer a single allele from the donor fragments into a recipient, a competent recipient cell. So next we'll take a look at how we can use these basic transformation steps to determine whether two genes are closely linked or not. So let's imagine that you exposed some competent recipient cells that have null mutations for both the A and the B genes. And you expose them to DNA fragments from a destroyed donor cell, or from many destroyed donor cells that have the wild type A and B, or the working A and B genes, or A and B alleles. So if the A and B genes are closely linked, what would you expect to happen? So here are your options. So as usual, please do pause the video now and commit to an answer before you start the video again. Okay, so pause it now. All right, welcome back. So the correct answer in this case would be D. All right, so you would expect some of the recipient cells to be showing the working versions of both the A and the B genes. So to give you kind of another picture to look at to help you visualize this, let's say that the A and B genes from the donor cell were actually about 2,000 base pairs apart. All right, and we're breaking that donor DNA into fragments that are around 5,000 base pairs long. All right, in that case, you would expect to see some of the recipient cells receiving a fragment that has both A and B in it, right? But only some of them would receive that. So only some of the recipient cells would be transformed at all, and only a few of those cells would receive a fragment that has both the A and B wild type alleles on it. And not only does it have to receive this whole fragment, not only does it have to receive a fragment that has both A and B on it, it also has to have recombination happen in such a way that both alleles get incorporated into its chromosome. So in other words, we'd have to have a crossing over event here and here for both genes to be put into the bacterial chromosome. All right. So that's why we would eliminate the possibility that all recipient cells that receive the A plus allele will also receive the B plus allele, right? One reason being that you could just get a fragment that has just A and one that has just B, or you can get a fragment that has both A and B and have crossing over events that only incorporate one and not the other. All right, so that's why only some of the recipient cells would have both of these wild type alleles. All right, so we would expect that if the genes are closely linked, we expect to see some recipient cells have the wild type versions of both genes. All right, but what if the two genes are very distantly linked? Let's say that they're 12,000 base pairs apart instead of 2,000. All right, what would you expect to see then? All right, so again, pause the video and decide on your answer. All right, welcome back. So in this case, we would expect to see way fewer A plus B plus recipient cells because if the two genes are really far apart, right, further apart than the largest fragments, meaning that the distance between the two genes is bigger than the size of the fragments, then you would never find both the A and B plus genes on the same fragment, right? It just wouldn't fit because it's too far apart and these fragments are too small. However, you would still possibly see a cell that has both the A plus and B plus alleles because you could get two separate fragments transforming a cell, right? And this is a very rare event though, because not only do you have to get both fragments into the cell, you also have to have a pair of recombination events put the A gene into the bacterial chromosome, and also a pair of crossovers here to put the B gene into the bacterial chromosome. All right, so that's why we would expect to see way fewer of these A plus B plus recipient cells if the distance between the two genes is much bigger than the sizes of the fragments, because we need two independent events here plus another two pairs of crossing over events to happen. All right, so if co-transformation between the A plus and B plus genes, meaning that the frequency with which we see both A and B in the recipient cell is more frequent than we would expect if these two events were happening independently, right? Then these two genes must be closely linked. All right. So So once again, so if you're seeing more A and B together than you would expect if they were happening independently, then we can predict that the distance between the genes is to some extent smaller than the sizes of the fragments. That's why it's more likely that two of them would appear on the same fragment. Right? So distance is smaller than fragment size is your conclusion. All right, so some questions that try to kind of hammer that home with some real numbers. All right, so let's say that in general, the A plus allele, when you're doing this kind of transformation experiment, it shows up in recipient cells with a frequency of 0.2. Okay, and then the B allele is transformed into the cell with a frequency of 0.15. So if we do a co-transformation experiment and we find that the A and B genes are co-transformed, meaning you'll find A and B together in a recipient cell at a frequency of 0.03, then what can you include? What can you conclude? All right. So once again, pause the video and commit to your answer. All right, welcome back. So you would conclude that the two genes are most likely very far apart, or at least further apart than the sizes of the fragments, right? The reason why is that if you take the probability of each allele being transformed independently, right? Probability for A plus is 0.2, probability for B plus is 0.15, then the probability of each of these events happening independently in the same cell, in the same recipient cell, would be the 0.2 times the 0.15. We want this event to happen and independently this event to happen. So we multiply them together, and that gives us a probability of 0.03. All right, so that's the co-transformation frequency we would expect to see if they're not linked closer than the sizes of the fragments, and that's exactly what we saw in our data, right? So this data would suggest that they are not closely linked, that the only way that they show up in the same cell is if they both get transformed into the cell separately. Okay, so our conclusion from this data given here is that the A plus and B plus genes are so far apart that they're only co-transformed when they're carried by two separate fragments, right? The fragments are never big enough to carry them both at once. All right, so let's change the number a bit. Let's say that we're starting with the same individual frequencies, but our co-transformation frequency that we observe in our data is 0.06. All right, what would you conclude then? So again, pause the video now. All right, welcome back. So in this case, we would likely conclude that the genes are closely linked, or at least linked closer than the size of the fragments. So let's look at why again. So again, the probability of each allele being transformed by themselves is 0.2 and 0.15. And once again, the probability of both events happening, if they're independently doing so, is, in other words, not closely linked, would be 0.2 times 0.15, which is 0.03. But the actual co-transformation frequency that we observe is a lot higher. It's double that, right? So it's 0.06 instead, right? So that suggests that the A and B genes, we're not just co-transforming them when they're coming in separate fragments. They can also be co-transformed together on the same fragment. So that's why we have a higher number of co-transformed cells than we would expect if they were independent. All right, so that's pretty much it. If you have any questions, you can feel free to email me or come by my office hours next week. Otherwise, have a great weekend, and thanks for taking the time to watch this.